Good morning students. This is the 7th lecture on the series Linear Programming. The title of today's lecture is the two-phase method. The two-phase method is an alternative method for taking care of the artificial variables in a linear programming problem. The outline of today's talk is as follows. We will learn the two-phase method, which is an alternative to the big M method that we studied in the previous lecture. That is, the two-phase method can take care of the constraints which are of the type greater than or equal to. So, we will study the working of the two-phase method. We will also look at the similarities and with the help of the exercises and examples, what is the difference between the big M and the two-phase method. We will look at some example and then some exercises. So, let us look at the same example that we studied during the previous lecture, so that we can make a comparison between the calculations of the big M method and the two-phase method. So, our problem is to minimize this 3-variable problem. Please write down this problem. Minimize z is equal to minus 3x1 plus x2 plus x3 subject to x1 minus 2x2 plus x3, which is less than or equal to 11, and the second constraint is minus 4x1 plus x2 plus 2x3 greater than or equal to 3. The third constraint is twice x1 minus x3 is equal to minus 1, and all the 3 variables x1, x2 and x3 should be greater than or equal to 0. So, this is the same example as we had done in the previous lecture. Now, as you know, in order to solve this problem, we have to convert it into the LP in the standard form. And what are the requirements for an LP into the standard form? Yes, the objective function should be of the maximization type. So, the objective function will become 3x1 minus x2 minus x3, because in the given problem it was of the minimization type. So, we have to multiply it with the negative sign in order to make it into a maximization problem. Now, let us look at each of the constraints one by one. Since the first constraint was of the type less than equal to, so we have to add a slack variable and we will call that slack variable as x4. So, the equation becomes x1 minus 2x2 plus x3 plus x4 is equal to 11. In this equation, x4 is a slack variable. Now, coming to the second constraint, since it was of the greater than equal to type, therefore, we have to subtract a surplus variable, and the equation becomes minus 4x1 plus x2 plus 2x3 and minus x5 is equal to 3. The third constraint becomes minus 2x1 plus x3 is equal to 1. Now, as you remember, the LP in the standard form must have the right hand side is equal should be greater than or equal to 0, but in the given problem the third constraint was having minus 1 in the right hand side, which is actually not allowed. Therefore, we have to multiply the entire equation, entire third equation with the negative sign, so that the right hand side becomes positive. Now, the slack and the surplus variables have also to be greater than or equal to 0. Now, the problem is we do not have a BFS to begin our algorithm, to begin our simplex method. So, what we need to do is we will look at an alternative method of taking care of the artificial variables x6 and x7 in the second and the third constraints, such that these artificial variables become 0, they vanish, and for this we will employ two phases. Let us try to understand what is the objective of the first phase and similarly what is the objective of the second phase. So, what we will do in the first phase, we will set aside the original objective function, we will set it aside and we will ignore it at the moment temporarily, and we will replace the objective function with another objective function, and that new objective function is nothing but the sum of the artificial variables. So, the artificial variables, since they have to be make 0 somehow or the other, so therefore, what we will do is we will minimize the sum of the artificial variables. What will happen is when the solution of the first phase is obtained, then that means that all the artificial variables have become 0, and that is what we want. We want that all the artificial variables should reduce to 0. Please note that this is possible only if all the artificial variables are greater than or equal to 0, because if they are not greater than 0, then the minimization will go something towards the negative, which is not allowed. Therefore, we have to make sure that the artificial variables are greater than or equal to 0 and their sum has to be minimized. This will ensure that at the end of the phase 1, we will have all the artificial variables becoming 0, and once this phase is completed, then we can start the second phase, and by bringing back the original objective function into our simplex table, so that by using the BFS which is obtained at the end of the phase 1, we can then proceed with the normal way in which the simplex calculations are done. So, let us see with our example how this happens. Now, as you know that in the phase 1, we will set up a temporary objective function, and what is that objective function? It is nothing but minimization of the sum of the artificial variables. So, the artificial variables are x6 and x7. As you know that just in the previous method we have also introduced x6 as an artificial variable in the first in the second equation and x7 in the third equation. So, we will call this objective function as w, so that we can differentiate between our original objective function which we called as z. So, our new objective function becomes minimization of x6 plus x7. Now, in the second and the third equation we have added the artificial variables. So, now we have a readily available BFS, and what is that readily available BFS? It is nothing but x4 is equal to 11. Why x4? Because x4 is a basic variable in the first equation. Similarly, the artificial variable x6 is a basic variable in the second equation. So, x6 is equal to 3, and similarly in the third equation x7 is equal to 1, because x6 and x7 are particularly have been purposely introduced, so that they can take care of the initial BFS which we want for our simplex calculations to work. So, we will solve this with the help of the simplex method, but before we do that we need to convert the objective function into the maximization form, and for that we will convert the objective function as minus w equal to minus x6 minus x7. So, I hope you have understood. We have got phase 1 where the objective function is the sum of the artificial variables, and we have a BFS which is nothing but x4 is equal to 11, x6 equal to 3, x7 equal to 1 and all other variables as 0. So, let us tabulate all this information into the table 1 of the first phase. So, phase 1 table 1. Here you will find what we have done is we have under the basis column we have written the basic variables. So, what are the basic variables? As I just now mentioned, they are nothing but x4, x6 and x7, and in the each of the columns under the variables x1 we write down the coefficients of x1. Similarly, under the column x2 we write down the coefficients of x2, and similarly x3 we write down the coefficients of x3, x4, x5, x6 and the right hand side. So, up till now all the entries are the same as that of the Big M method. However, there is a difference in the topmost line. You will observe that since the objective function is different now, we have set aside the original objective function and we have considered a new objective function which is nothing but the sum of the artificial variables. So, our objective function minus w has coefficients corresponding to x1, x2, x3, x4, x5 and all these are 0. So, they have to the corresponding entries in the top line over here, this should be 0. So, this top line has to be 0. Only the entries corresponding to x6 and x7 they will be minus 1, right. Also, we have to make sure that the corresponding entries of the basic variable, that is x4 is 0 in the objective function, x6 has to be minus 1 and x7 has to be minus 1. So, like this we have prepared the table number 1 of the first phase. We can see that the basic feasible solution for the first table is x4 is equal to 11, x6 is equal to 3, x7 is equal to 1 and all remaining 0. So, next what we need to do is we need to start our simplex calculation by computing the deviation rows. And how do you compute the deviation rows? You have to subtract 0 minus this vector multiplied by this vector. Let us see how this is done. Here they are. These are the calculations for obtaining the deviation rows. You will see 0 minus 0 minus 1 minus 1 multiplied by 1 minus 4 2. So, the corresponding entry becomes minus 6 and that is what we have written over here. So, this first entry is minus 6. Similarly, the second entry is nothing but 0 minus 0 minus 1 minus 1 multiplied by minus 2 1 and 0 and this comes out to be 1. So, this entry is 1. Here is this entry 1 and then comes the third entry 0 minus 0 minus 1 minus 1 1 2 1 and this comes out to be 3. the next entry is 0 minus 0 minus 1 minus 1, 1 0 0 which comes out to be 0. Similarly, 0 minus 0 minus 1 minus 1 multiplied by 0 minus 1 0 which comes out to be minus 1, and then the next entry is minus 1 minus 0 minus 1 minus 1, 0 1 0 which is equal to 0, and similarly the last entry is minus 1 minus 0 minus 1 minus 1 multiplied by 0 0 1 which comes out to be 0. Before I proceed, I would like you to make an observation. You will find that the entries in this deviation rows corresponding to the basic variables. Just let us look at the these entries. I mean that now in this table we have x4 as the basic variable. So, what is the entry of the basic variable in the deviation rows? It is 0. Similarly, for x6, because x6 is a basic variable, so therefore, the entry in the deviation rows corresponding to x6 is also 0, and similarly for x7 the entry in the deviation rows is 0. Now, this is not a chance, this will always happen that whenever you compute the entries in the deviation rows, they will be 0 corresponding to the basic variable in that particular table. Therefore, all these entries corresponding to x4, x6 and x7 is 0 in the deviation rows. Okay, so once we have computed all these entries, next we want to look at the largest of these deviations. Why we need to do that? We need to do that because we want to see which variable should enter into the basis, and as you can see out of these deviations the third entry, that is the value 3, this is the largest, and this indicates that x3 should enter into the basis. So, the criteria for entering the basis is largest deviation rows, and therefore, x3 has to enter the basis. Next comes another decision which we have to make, that is we want to find out which variable should leave the basis. So, what are we going to do? Yes, we are going to compute the minimum ratio test. So, the minimum ratio tests is obtained, that is we will look at the right hand side which is nothing but 11, 3 and 1, and similarly we will look at the pivot column which is nothing but 1, 2 and 1, and we will look at these ratios, the minimum ratios. So, what are the ratios? 11 upon 1, 3 upon 2 and 1 upon 1, and what do you conclude? You conclude that out of this the minimum is 1, and since minimum is 1, this means it is corresponding to the variable x7, and therefore x7 has to leave the basis. So, in the first table we find this cell is the pivot, and this has to be made 1, and the remaining entries in that column have to be made 0 with the help of the elementary row operations that we studied last time. So, that is what we are going to do. We will perform the elementary row operations like this, that is right. The first row R1 has to be replaced by R1 minus R3, because we have to make this third column as 0 0 1. the last entry 1 is already there, so you do not need to do anything. Only thing is you have to make the first entry as 0 and the second entry as 0. So, the first elementary row operation is R1 has to be replaced by R1 minus R3, and similarly the second row, that is R2, has to be replaced by R2 minus 2R3. Once you apply these elementary row operations, you will get a column like this 0, 0 and 1, and that is what you wanted. So, the resulting table will look like this. The third column, as you can see, is 0, 0, 1. That completes the first iteration. Now, again we will do the same procedure, we will repeat, and before we repeat that, we have to make sure that the entry corresponding to the first column, that has to be changed, because now x3 has entered into the basis. So, here we need to write the corresponding objective function value of x3, and that is 0. So, in the first column we will write 0, minus 1 and 0. The first column is 0, minus 1, 0, and the corresponding BFS becomes x4 equal to 10, x6 equal to 1 and x3 is equal to 1, and remaining zeros. Again, as before, we will do the calculations for obtaining the deviation rows. And what are those calculations? These are the calculations. As before, you can see that all those entries which are corresponding to the basic variables, that is x4, x6 and x3, automatically they will become 0, and the remaining entries you have to calculate as before. 0 minus 0 minus 1 0 multiplied by 3 0 minus 2, which comes out to be 0. Similarly, 0 minus 0 minus 1 0 multiplied by minus 2 1 0, which is equal to 1, and similarly 0 minus 0 minus 1 0 multiplied by 0 0 1, which comes out to be 0, and 0 minus 0 minus 1 0 multiplied by 1 0 0, which is 0, and similarly the other ones will become minus 1 0 and minus 3. Once all these deviation entries have been calculated, then we need to see which one of them is the largest, because that is the criteria for making sure that a particular variable is to enter the basis. And what do we find? We find that the entry in the second place, that is 1, is only the positive 1 and it is the largest. So, this indicates that the variable x2 has to enter the basis. We have to next take a decision regarding the fact that which variable should leave the basis, and for this we need to perform the minimum ratio test. The minimum ratio test is the ratios between the right hand side, which is nothing but 10, 1 and 1, and the pivot column, which is nothing but minus 2, 1 and 0. Now, you will observe that in the pivot column the first entry is minus 2 and the last entry is 0. Now, these two entries have to be avoided. The minimum ratio test has to be performed only with the positive entries. So, in this particular case we are left with only one choice, that is the second entry. So, the minimum ratio will become 1 upon 1 and that is nothing but 1. So, there is no other choice in this particular case, and automatically this variable corresponding to the second entry, that is x6 is the living variable. And with this decision, let us look at this table again. Here you are, you find that x6 is the variable which should leave the basis, and that is the reason why this particular cell is highlighted to indicate that this is the pivot. Okay. And again we will perform the elementary row operations in order to make this pivot as 1 and the other entries as zeros. So, what are the elementary row operations? You need to perform only one elementary row operation, that is right. That elementary row operation is R1 has to be replaced by R1 plus 2 R2, and with this operation our pivot will become 0, 1 and 0. Please note that the second entry was already 1, so we did not need to do anything about it. The third entry was already 0, so we did not need to do anything about it. Only problem was with the first element. So, first entry we wanted to make as 0, and that is the reason why we applied this elementary row operation and made this particular pivot column as 0, 1, 0. Thus, we come to the table 3 of our phase 1, and what do you find? Please note, you find that in this table both the artificial variables are not there. So, you have observed that during this table 3 all the artificial variables have disappeared, because what is our BFS? Our BFS is x4 is equal to 12, x2 is equal to 1 and x3 is equal to 1, and all others as 0, all other as 0, and all other means x6 and x7 also are 0, and that is what we wanted. So, what is the use of this phase 1 has been achieved. Remember, our objective of applying the phase 1 was to make sure that these artificial variables disappear from the basis, and that is what has happened. So, phase 1 is complete because the value of the objective function is also become 0, and the artificial variables have disappeared from the basis. That is what we wanted. Next we will come to the phase 2. So, this is just an explanation. The value of the temporary objective function has become 0, artificial variables x6 and x7 have disappeared, and this indicates that the phase 1 is complete. So, we can say that now phase 1 is complete, and now we can move on to the second phase. So, now we can bring back our original objective function, which was maximization of z is equal to 3x1 minus x2 minus x3, and we can start the phase 2 with the help of the BFS which we have obtained at the end of the phase 1. So, at the end of the phase 1 we had this BFS x4 equal to 12, x2 is equal to 1, x3 is equal to 1 and all others as 0. So, now we can start the phase 2. However, before starting the phase 2 we will observe that the artificial variables are x6 and 7, x6 and x7 are both 0. So, they are not required, they are redundant, and we do not want them, so we can just drop them, we can just ignore them, and that will help us in reducing our calculations since they are 0. So, what we are going to do is we will remove the two columns corresponding to x6 and x7, and therefore, our calculations have decreased to by removing these two columns corresponding to x6 and x7, our calculations have reduced to quite an extent, and you will observe that in the top row here, in this row we have brought back the coefficients of the original objective function 3x1 minus x2 minus x3 etc. And the phase 2 table 1 has all these entries as same corresponding to these entries in the columns and the rows. All these entries are same. What is the difference? The only difference is this top row has the coefficients corresponding to the original objective function, as well as these entries 0, -1 and -1. Why are these different? Because they are the entries corresponding to the basic variables in the objective function, and since now we have brought back our original objective function, so therefore these entries have also to be changed. The BFS, the starting BFS is nothing but the same, that is x4 is equal to 12, x2 equal to 1 and x3 equal to 1 and all others zeros. So, what we will do is we will again calculate the deviation rows, and mind you, these deviation rows will be different from the deviation rows of the table number 3 of the phase 1. Why will they be different? Can you think why will be they different? Yes, they will be different because they are obtained from the objective function, and since our objective function has changed, therefore these entries will also change. And how are they calculated? Let us see. Yes, here they are. They are calculated as usual, 3 minus 0 minus 1 minus 1 multiplied by 3 0 minus 2, which comes out to be 1. Similarly, minus 1 minus 0 minus 1 minus 1 multiplied by 0 1 0, which is 0, and obviously as I said, this is a basic variable, x2 is basic variable, x3 is basic variable and x4 is basic variable. So, therefore, their entries have to become 0. Only the non-zero entry will be the last one, the first one and the last one, and the last one is nothing but 0 minus 0 minus 1 minus 1 multiplied by minus 2 minus 1 0, which comes out to be minus 1. And this tells us that amongst these deviation entries, the entry number 1, the first one, that is the largest, and this indicates that x1 should be the entering variable at this particular stage. Next comes the minimum ratio test for determining which variable should leave the basis. Now, you will observe that the right hand side is 12 1 1, whereas the pivot column is 3 0 minus 2, and as you know that 0 has to be excluded, minus 2 has to be excluded, and therefore, what will happen is we are left with only one choice, that is the 12 upon 3, and there is no other choice. So, therefore, this means that x4 is the living variable. The first entry, that is x4, is the living variable. Now, we want to make this as 1 0 0. The first column has to be 1 0 0. Therefore, accordingly we will apply the elementary row operations. So, what are the elementary row operations? The first row, that is R1, has to be replaced by R1 upon 3, that is it has to be multiplied by 1 by 3, R1 has to be multiplied by 1 by 3. Can you tell why this is so? This is so because the coefficient of this entry is 3, but we want to make it as 1. So, in order to make it as 1, we have to divide the entire row by 3. Similarly, the other row operations, that is R3, R3 has to be replaced by R3 plus 2 R1, this will make it as 0. you will observe that R2 corresponding to R2 the entry is already 0. So, nothing has to be done. In our previous table, see here the first column over here is 3 0 minus 2. So, 3 has to be made 1, and how will you make it 1? You will divide the entire row by 3. So, the first entry will become 1, second entry is already 0, you wanted it to make it 0, it is already 0. So, you do not have to do anything about it. The third entry is minus 2. So, you have to apply the elementary row operations in such a way that this minus 2 becomes 0, and that is what we have done. So, this means that our pivot column has become 1 0 0, and that is what we wanted. So, the resulting table number 2 for the phase 2 looks like this. Now, you will observe that in this table, as usual, we will compute the deviations, and the deviations tells us that the first 3 entries are 0, whereas the fourth and the fifth entries are negative. And as you know, what is the stopping criteria for the simplex method? Yes, the stopping criteria is that all the entries in the deviation rows should either be 0 or should be negative, and that is what is happening here in this particular table. All the entries in the deviation rows are either 0 or negative. This indicates that the stopping criteria has been achieved, and therefore, this is the solution to the given linear programming problem. And what is that solution? The solution is the current BFS. What is the current BFS? x1 is equal to 4, x2 equal to 1, and x3 is equal to 9. So, I hope everybody has understood what is the basic idea behind the two phase method. I have a question for you, and the question is, what are the differences and the similarities between the big M method and the two phase method? During the calculations of the big M method and the two phase method, do you observe any differences? Do you observe any similarities? And we have to identify what are those differences and similarities. So, in my next lecture, I will reply to this question, but at the moment I want you to give it a thought to identify what are the differences and what are the similarities between the big M method and the two phase method. So, please think it over, compare the calculations of both the methods and see what are the similarities and differences. So, as an exercise, I would like you to solve this linear programming problem. So, please solve this problem, you can write it down, solve the given linear programming problem with the two phase method, and also I want you to compare your calculations with the big M method. So, the problem is minimization of x1 plus 2x2 plus x3, and it has two constraints subject to 2x1 plus x2 plus x3 less than or equal to 2, and similarly 3x1 plus 4x2 plus 2x3 greater than or equal to 16, and x1, x2 and x3 have to be greater than or equal to 0. So, I hope you can do this question with both the methods, the big M method as well as the two phase method, and keep your calculations side by side, put them side by side and see what are the similarities and the differences, right. Thank you very much.